So our second speaker will be Huiling. All right, so Huiling is currently a PhD student in the Computer Science and Electronic Engineering department at Hunan University. So her research primarily focuses on the hardware security of mobile devices, with particular interest in what's the topic today, which is actually the electromagnetic radiation and also side channel attacks at the same time. So I guess today she is going to talk about how having headphones will actually make you actually vulnerable to this EMR like signal attacks. Yeah. So yeah, take the stage.
Okay. This is Huiling Chen, a PhD student advised by Professor Wan Changjing and Professor Yupeng Hu. I'd like to talk about our work. Eavesdropping black box mobile devices where audio amplifies EMR, which is a joint work with Nanjing University of Process and Telecommunications and the University of Texas at Arlington. Speaker is the hardware component responsible for producing sound output. Is widely used for mobile devices, such as smartphones and tablets. The speaker's sound emits to the open space can be recorded by a microphone. The traditional audio eavesdropping attackers show that speaker sound can potentially be eavesdropping on by malicious microphones. In recent years, some novel audio eavesdropping attackers demonstrate that non-microphone devices can be exploited to recover speaker sound via side-channel leakage, such as motion sensor, telescope, and camera. Protecting users' private audio is critical, and we aim to explore the feasibility of eavesdropping on mobile devices via side-channel attack when it is connected to a headphones. And the headphone is the micro speaker, which it works. It can have no sound emitted to the open space nearly. Prior works reveal that the eavesdropping threats of wireless headphones, side-channel leakage, such as electromagnetic radiations and magnetic signal from wireless headphones micro speaker can be exploited to recover users' private audio, while the security risk of wired headphones has not yet been exploited. Therefore, we aim to investigate the eavesdropping threats of headphone-plugged mobile devices. Our goal is to evaluate the new eavesdropping threats of headphone-plugged mobile devices and to mitigate the security risk of using headphone-plugged mobile devices to listen to private audio. Our attack explores the electromagnetic radiations of mobile devices to recover victims' private audios. In this attack, when the victim plays sensitive audios using wired headphones, the smartphone side will passively emit electromagnetic signal to the open space. Therefore, attacker can use head EM sensor to collect the signal and transmit this data to a remote audio recovery server. To achieve this attack, we face two challenges. The first is signal acquisition. What types of EM sensors can be used to measure a device's EMR in a daily mobile usage scenarios? The second is audio recovery. How to recover intelligible audio from EMRs when the attacker has no prior knowledge about the target devices. To address these challenges, we foster research on the working principle of wired headphones. while the headphones are powered by the mobile device's audio control motor to produce sound. In particular, the audio control motor generates an original audio current with a low amplitude. Then the audio current will further be amplified to drive the micro speaker to vibrate. In this process, intense fluctuation in currents occur, leading to electromagnetic radiation leakage. Following the Maxwell's equation, the radiated EM signal ET is equal to UC multiplied AT plus AC multiplied gain. From this equation, we can find that the ET is proportional to the input audio AT. Therefore, they have the same signal pattern, so it is feasible to leverage the EM side channel to recover the headphone-plugged mobile device's audio. Moreover, the headphone will play as an antenna to expand the EMR radiation distance. Based on this conclusion, our attack design is composed of two steps. The first step is EMR measurements. How to sense the EM signal and what sense device should be used. We observe that the electromagnetic field can result in an electrical potential on a conductor, and the induced voltage Vt is proportional to the EM signal ET. Therefore, we can use the conducting wire as the EM sensor to measure the EM signal. The procedures of EM measurements are divided into three parts. They are signal sensing, signal readings, and signal processing. The second step is audio recovery. For this step, we need to answer two questions: how to remove noises and how to convert extracted EMRs to audio contents. In the pre-processing, three procedures will be conducted. The first is to use band-stop filters to remove noises from power cables. The second is to remove noises beyond the human hearing range. Finally, we strengthen the audio-related signal by normalization. But in door environments, besides the targeted EM signal, other electric devices, such as light, Wi-Fi router, can also emit EM signal, making the measured EM signal contains environmental noises. Well, the environmental noises are typically random and have a broad spectrum. It cannot be easily eliminated using traditional filtering techniques. Therefore, we employ discrete wavelet transform techniques to process the EMRs and remove environment noises. However, in practice, the extracted ET is not proportional to AT due to the amplified effects, which makes it difficult to extract audio AT. To leverage the machine deep learning models to map ET with AT could be an effective approach. But to build training-based model requires a large amount of collected data in advance of the attack. By analyzing the frequency of the ET, we find that the high power terms present themselves as harmonic distortions and cross products in spectrum. Moreover, we observed that the audio components groups well. The distortions is randomly distributed in the spectrogram. Based on this observation, We propose a clustering algorithm. Its name is DBSCN to extract the grouped audio signal from the EMR's STFT spectrogram. We conduct a correlation analysis to verify the extracted audio. The results indicate that the extracted audio is similar to the original input audio. By inputting the extracted audio into the speaker, it can be recognized by human hearing and commercial speech recognition tools, such as the Microsoft audio-to-speech tool. Our attack system includes two procedures. They are signal sensing, signal readings, data transmission, and audio recovery. The performance of our proposed eavesdropping attack is evaluated via the following metrics. The PSNR and the MOSFET is to evaluate the audio quality, and the STOI and WER is to evaluate the intelligibility. Both and for our evaluated mobile devices, it includes smartphones and laptops. And moreover, 6 headphones are also evaluated. The overall performance indicates that this attack can achieve the lowest at 7.44% and average MOSFET, STOI, WER, and PSNR at 2.83, 0.75, and 17.83%, and 20.85 respectively. Moreover, we evaluated 4 impact factors of our attack. The first factor is physical obstacle. We selected 3 types of materials. They are wood, plastic, and wool, respectively. The results indicate that EMR can penetrate all these obstacles without significant energy loss. The second is volume. A higher volume setting increases the risk of audio leakage. The third factor is distance. The effectiveness of the attack decreases as the sensory distance increases. The last factor is relative angle between the EM sensor and the victim's devices. The results shows that all angles can be used to conduct an audio eavesdropping attack. And this is responsible disclosure. We have contacted the product security team at Huawei and Dell and so on. And we received their feedback, and the Huawei company has reproduced our attack. To conclude, our paper proposed a new audio eavesdrop attack that explores electromagnetic radiations of mobile devices amplified to recover victims' private audio. And we also designed an audio recovery algorithm that requires no prior knowledge about the target device to extract audio contents from EMRs. And finally, we evaluated the effectiveness of this attack on 11 mobile devices and 6 headphones, and reported the security threat to leading manufacturers. And that's all. That's my idea of our work. For more details, please refer to our paper. And thanks for your listening.
Okay, questions? I don't know who's the first. Probably you at first. Okay, then Ryan maybe.
Thank you. Thank you for the great work, Murtaza Jadliwala, University of Texas, San Antonio. Couple of quick questions. On the practicality of your attack, it appears that at a distance of just 100 centimeters, your accuracy really goes down. Do you think the attack is practical? Because if 100 centimeters, I can just see that someone is sensing.
I cannot get this.
Do you think your attack is practical? Because at 100 centimeters,
the black box mean we use the algorithm that no need the training data, so we think it's a black box method to recover the audio.
But the attacker, the person, the target can see the sensing device at such a close range.
Because the EM signal, it is a fundamental signal, and for the above presentation, we have verified that the signal is very similar to the original audio. So we don't need the training data, so we can recover the audio.
I'll take it offline. Yeah.
So he's asking about distance.
Distance. The maximum distance is 1 meter away.
But the sensing distance is just 100
sensing distance.
Sensing distance 1 meter?
Yeah. So we use the EM sensor. It has a small size, so it can be handled in the victim's surrounding environment. And the sensor, it has Bluetooth or Wi-Fi connections to transmit the data to the remote attacker.
Okay. Okay. Thank you. I'll let others ask questions. Thank you.
Okay.
Have you thought about to make the distance to be longer?
In the next paper, I will to improve the hardware setting and to expand the distance.
Ryan, you want to try?
Ryan Gertis, Virginia Tech. Which countermeasures did you consider? For instance, the headphones. Did you experiment with magnetically shielded headphones?
Headphone, I haven't taken it. The headphone is our daily used headphones.
That's defense, like shielding. So he's asking whether adding some shielding of the phone. Less shield.
So the headphones can be designed so that the magnetic field in the headphones doesn't interact with other devices like televisions and laptops and so forth. And also you could shield the audio cable itself, as well as applying some RF chokes maybe to the device itself. Have you considered these countermeasures? How does the attack fare?
In our experiment, the headphone wire it can play as an antenna to expand the distance, so we can sense the EMR signal in a long distance. If we haven't the headphones wire, the distance will shorten. Defense. As far as now, the defense we can only using the hardware setting to defend this, such as use a metal piece to cover the leakage.
Okay. Yes, that sounds reasonable. Thank you.
Thank you.
So that's